So today I'm going to talk about technology applications for seismic events. Earthquake early warning has been in the news quite a bit in the past couple weeks, and I'm going to talk a little bit about that. But there's a lot of other technology applications for earthquakes, seismology, buildings, engineering that you probably haven't heard about. And so I'm going to try to give an overview of all of the neat tech and science that goes into the study of seismology, and that way if you want to learn more about any of these topics, either jump right in. I am not shy, so ask questions, interrupt me, no problem, and I can go into things in a bit more detail. And I have one or two longish videos, so it'll be kind of like when the teacher rolled out the AV card for class one day, but they're really good and informative, so I hope you enjoy them. So before we get started too much and all the tech, I kind of wanted to give a small schematic about what are we actually looking at, what are we measuring. And so an earthquake is a set of energy waves. There's different wave fronts. The first one is a P wave, second one is an S wave. We're really creative, we call them the primary and secondary waves. Those make up the body waves of the signal, and then you have a series of surface waves. So when I'm talking about measuring an earthquake, this is the sort of textbook signal that you're going to get. Now, obviously in real life, the signals don't always look this pretty and this spread out and this well defined, but just to give you sort of a base thing to have in your brain while I talk about all of these other things, here you go. So earthquakes have been around since the Earth has been around, since people have been around to feel them. We haven't always had the technology to characterize them or even know where they're coming from. So when you're talking about really ancient civilizations, you have the folklore aspect, where ancient Japan thought that there was this gigantic catfish that was like, smacking the earth and causing all of these ruptures. And it wasn't until the Eastern Han Dynasty, where a scientist named Zhang Heng created the first ever seismoscope. Now this is called a seismoscope and not a seismometer or a seismogram, because this apparatus has no sort of written recording capabilities, so it's not a graph, and it's not a seismometer because it has no temporal calculations or recording. And so what you're seeing here is a reproduction of the original seismoscope, which was created in 132 AD. And it's an urn that has a whole bunch of Chinese dragons coming off of it. And each one of these dragons is holding a ball. And then there's a whole bunch of frogs with open mouths at the bottom. And so what would happen is the earth would shake, a dragon would drop a ball into a frog's mouth, and you would be able to tell which direction the earth had moved. And so this is really high tech. This is like crazy. This is the first time anybody had ever done anything like this. And sitting in Silicon Valley today, you can be like, okay, that's kind of rudimentary. But when you don't even know what you're feeling, where the sensation is coming from, this is actually a really cool feat of technology. And so then nothing happened for a really, really, really long time, until the Lisbon earthquake of 1755. This is an image of a copper engraving that's at the Museu de Cidade. I do not speak Portuguese, and so I'm probably butchering that, but it shows you the destruction of the city of Lisbon due to the earthquake and the incoming tsunami. And so this earthquake was really important because it was the first time that people really, really, really got serious about, okay, we need to figure out what's going on here. And you have your sort of famous physicists and other scientists of the day starting to think about the physical world in new ways. And so they started trying to think about earthquakes in new ways. Is this something that starts some particular place on the earth and is affecting me over here? Or is this something that the earth is globally doing? When you don't even know that piece of information, it's really hard to design technology to answer questions. But thankfully, they started to figure these things out quite rapidly. And so in the space of about 100 years, you get not only a bit of rudimentary science and sort of background calculus and everything you need to actually make good instrumentation, and you start getting instruments. And so here are a bunch of sketches of some of the really early seismic instrumentation. And again, this is very heavy, state-of-the-art stuff. These are the people locked in their rooms, only tinkering. So on the left, you have a schematic from Ford. It was in 1844. And this is an inverted pendulum. And you're going to hear me talk about, and I want you to keep in mind that a lot of the seismic instrumentation technology relies on either pendulums or springs. These are things that are very easy to characterize. They have very defined behavior for very small movements, and this makes them great to use as instruments. So this is an inverted pendulum, and so as the Earth moves, you can look at the displacement that the pendulum is making and then be able to translate that into some sort of terrestrial movement. On the upper right-hand side, you have an instrument from Mallet in 1852. This is an instrument that nowadays would never make it past the drawing stage. OSHA would be cracking down on this thing. You would never get it past any sort of review board whatsoever, because what this instrument involved was two viewfinders, C and D. B is a gigantic basin of mercury that's just open to everything. And what Mallet did is he used to set off explosives nearby this instrument and watch through these viewfinders where he put his face right by this bowl of liquid mercury that's being disturbed by explosives to sort of watch what the movement of a viewfinder, sort of crosshairs and see, was doing in the reflection of the mercury pool. So again, these sort of crazy tech ideas thinking way outside the box. It would probably get shut down today, but we have it because it was done in the 1800s. In the bottom right-hand corner, there's an instrument by Ewing, and this is sort of the granddaddy type of instrument that you have. Around the time of Ewing, the late 1800s, you have a lot of different kinds of instruments of this type or similar types, but this is just one good sketch of this. So this is a horizontal pendulum. And so that big, long sort of pivot arm that you have there is a horizontal pendulum and has a little tiny pin, like almost a needle, at the F position. And so this thing is perfectly aligned by these screws, so it's perfectly level. And then M is a drum, and it's a smoked drum. So some poor grad student in the bottom of the lab used to have to pour smoke onto this glass and end up looking like a chimney sweep. And what would happen is, due to ground movements, this particular one would be measuring sort of vertical motion, and it would use that little pin to etch a line in that smoked drum. And so now you actually have a written record that you can analyze after the fact. And one of the most entertaining aspects of this type of instrumentation, especially with the smoked drum, is I have a colleague who actually still, when he was in grad school, had to go down to the basement and smoke these drums. And so it gives you an idea of how sort of slowly the technology evolves. And this is for a couple of very good reasons that I'm going to get into shortly. Just for sort of nostalgia reasons, I love this photo. This is a photograph of a man using a developorter, which inputs data from a whole host of different stations they're looking at a particular time and puts it on a continuous reel of film. This is generally something like microfiche. And then you see that he's there with his ruler, actually measuring the peak-to-peak distance of different features in the seismogram, and probably also he had to measure the amplitude so that he can start doing his pen on paper analysis of the earthquake. And this was really, again, huge high tech, because this, you could give information. You could look at these film imprints only 11 minutes after an event. And it's right on a monitor, and you can easily see, because you couldn't do stuff like that with these smoked drums, right? If you did too much, you'd start smudging your whole record. And so you've seen this sort of, what we would think of today as sort of primitive instrumentation. But the problem with trying to even develop any sort of seismic instrumentation is that it is a complex problem. Number one, you're having to cover about 8 orders of magnitude of bandwidth. So this is a very large bandwidth problem. Nowadays, we can use different instruments that are better suited for looking at different pieces of that bandwidth, but you still, need to look at the whole signal. The other problem is that you need to record a very large dynamic range. And so you're looking at ground motion from a few nanometers per second squared up until 10 G. And that's also very difficult to put in one instrument, especially if you're talking about instruments being created in the 1800s. But those are the easy parts of this complex problem. The difficult part of this complex problem is you have to do all of that while everything is shaking, including your reference frame. And that's the kicker. If you're going to try to figure out what the speed of a car is going down the road, what do? You have a radar gun, and you stand still, and you watch the car as it's moving past. GPS is done from a fixed location on the ground. If you have your whole instrument shaking like this, and the thing you're trying to measure is shaking like that, but not necessarily in the exact same way, it's very hard to decouple both of those two movements and know that you are measuring the machine response and not some other phenomenon.
You're measuring speed. You're measuring acceleration, not the speed. It's easier.
It's a little easier, but we also do, number one, you could do integrations to get velocity, because really you want to get position at some point. But yes. So nowadays we have more fancy instruments because we know that we can, we get an inertial mass and we can damp it. And then it's not as influenced by the whole shaking of the world. And you use different sorts of electronics to amplify the parts of the signal you want to do. You can do, I'm just losing my words, you can do sort of like capacitance, damping, and you can put things in evacuated chambers, so now you don't even have atmospheric effects hampering your instruments. And so these are the sort of fancy things that we can do today. So today, if you were looking at something like the Napa earthquake, here you go. We have a bunch of stations signified by these little black squares. And the data that's recorded on all of these various stations can be seen to the right. Some of them, the data and the model follow the station very well. Some of them follow it less well. And this can be for various reasons. But the idea is to get a bunch of different instruments that can look at all of these little minute changes in the ground and record a full spectrum so that then you can do what's called a moment tensor solution to look at the full profile of the earthquake. And so this is what modern seismology is all about, and we're constantly trying to push the limits of that. So how many people woke up for the South Napa earthquake? You were already awake. Oh goodness, that was early. Yeah, so that was the South Napa earthquake was the largest earthquake in the Bay Area since Loma Prieta. And so this was a big deal for science in the area.
These waves are tensors or something? Is there compression or twisting or which direction?
Right, there's all. So the
What was the
first,
question?
So he was asking if it was like these are tensor calculations, so are these compressional waves or they're torsional waves? And so it's kind of all. The first wave front is a P wave, it's a compressional wave, and I wish I could put this, I almost put this figure in. But, so that's one coming, the earthquake starts underground, and so the biggest P wave is the one that's coming under you, so vertically, so you get a compression wave up like that. The second wave front is the S wave, and these are the transverse waves. So these are the ones that start going side to side, and so that is the wave front that begins the damaging shaking wave front. It's a compressional wave, for all intents and purposes, not going to do much. Then you get the rest of the surface waves, and those are Rayleigh waves, Love waves, and those are the ones that can do rolling motions like this of the ground. And so then you start to get a stacking of all of these different translational and rotational.
You use a Fourier transform to break them all apart and their various components.
Mm-hmm. Yes?
On these graphs that you're showing up here, what's the difference between the red lines and the black lines?
So I'm going to get these backwards because I didn't get this, but one is the actual signal from the recording of the station. The other one is the model. So when you're trying to do a moment tensor solution, you're trying to fit the line to a model that not only makes sense mathematically, but also makes sense geologically speaking. You don't want to solve a moment tensor solution that tells you that you have like a subduction zone fault going right through Hayward, because that's not physically sensible. You also don't want, so this little ball diagram with the 4 quadrants is what we call a beach ball diagram. So it tells you that the earthquake is moving the plates side to side as opposed to like a thrust earthquake, which moves them vertically with respect to one another. So you also want something that has a very nice orientation. It makes sense that if you have a strike slip situation that it would go along the known fault line and not off somewhere else. So you want to make the best fit to the model and the data that's sensible. Sometimes it doesn't follow exactly. You're going to do the best you can, but that's what we're sort of looking for. So these stations on the right are the sort of the ones that did, I think these are the ones that did the initial moment tensor solution. There's a computer program that runs this quickly, and then the seismologist on call gets a page, and you have to go and verify all the information and solve your own moment tensor and compare it to the one that was done automatically to upgrade it. And my most happy moment of the next earthquake was the fact that I was on call until midnight that night. And the pager got turned off, and it was not my problem. So, awesome. Okay, so earlier I talked to you about inverted pendulums as they have to do with measuring earthquake motion, right? So if you move the earth from side to side, you have it, sorry?
That's maybe a silly question, but why you don't measure the pressure instead of the wave? The pressure, the vertical pressure that you describe. The root instead of the consequence.
I actually have no idea. I don't have a good answer for that, but I can ask somebody. Okay, so we talked about inverted pendulums. So if you move the earth from side to side, the inverted pendulum is going to swing side to side. And so this, if you damp it, does a very good thing. Well, now we live in the modern age where we like to build skyscrapers, which are gigantic inverted pendulums, right? And so what's going to happen to gigantic buildings if you start moving the earth from side to side? Well, people on the 80th floor are going to go, right? Because no amount of steel bracing is going to help you in that realm. And so engineers can do really cool things because they know technologically what's happening in an earthquake. Because on a lot of these very large buildings, they have put all sorts of accelerometers and different sensors on different floors and done huge shake table tests. And this is the bread and butter of building construction for large structures in areas where you have high incidence of earthquakes. is they measure this, and after every single major disaster, what happens? All the engineers look at all their data, and we get a huge change in the building codes, right? Okay, so Taipei 101. Over half a kilometer tall building. So what they did to counter the fact that they have a giant inverted pendulum that is near fault zones, they have put their own pendulum inside the inverted pendulum to counteract the effects and in effect damp their own building. And so they have mounted on this building this giant golden snitch looking thing here. It is a 5.5 diameter metallic orb that's made actually of a bunch of stacked metallic discs on top of each other. It weighs 660 tons. And I'm going to show you what I feel is a frightening video. So this is Taipei 101 during the Sichuan earthquake. Okay, so they have an observation deck on this floor. You can go and actually look at the giant pendulum. There's a person standing right there, so you can see the gigantic size of this thing. And then the earthquake hits. And somebody is standing up here filming this thing as it starts to move. So that's a 660-ton ball that is swinging in the air. And you see it has all of these, I've lost my word here, the braces to, it's a pipe that goes in and out. To make sure, this thing is not actually going to swing outside the building and break through the floor and go rolling down the countryside. But I just feel like not only are you feeling sort of earthquake effects, but you're watching this giant ball swing back and forth. That just frightens me just a little bit.
In a place like San Francisco, do they network all these buildings as ad hoc seismometers for real-time sensing?
So a lot of the buildings in San Francisco, I'm for sure about the Trans-America building, but a lot of the other skyscrapers, they put sensors on every couple of floors so that they can watch either normal vibrations.
Does that network like into your center so that it essentially increases the density of sensors in the area?
Not right now, no.
Okay.
A lot of the sensors that are put in buildings are just either put there temporarily by the engineers, or they're just geophones, or they're big sensors. But these are the sort of things that they use to look at normal modes of the building, different harmonics you can get by having, the 14th floor being just at the right sweet spot. Okay, so that is sort of building engineering. Now I'm going to completely switch.
What happened to that building? Did it actually work, that pendulum thing?
Yep, it worked. It's still.
Did it work better than the other buildings? Was there like a...
Well, I don't think anywhere in Taipei there's a building quite this tall at this time. This was at the time the largest building, the tallest building in the world. I think now Dubai,
They didn't put it in
cloud
the
building is higher, but I don't think there's anything quite like this in that building. Okay, so I'm going to completely switch gears and I'm going to do this quite a few times during the talk because I want to show you the breadth of the tech and not solely focus on one area for too long. So our lab, we're a university and we do seismological research not only for scientific interest and the drive to know more about the world, but also we're an educational institution and we like to educate people. So one of the cool tech things that we're able to do now that everybody has a smartphone in their pocket is create smartphone apps. And so we have, our first app was called MyQuake. And this app is fun. I was talking to somebody right before the talk about the coolness of this app. This is only available on iTunes Store at the moment. We're working on an Android port, but that hasn't happened quite yet. And this is a very cool educational tool. One of the biggest problems with trying to reach the public on earthquake hazard, risks mitigation, the great shakeout that's held every year, drop, cover, hold on, is the fact that when you have a very large rupture happen and everybody's like in the middle of it, like, oh yeah, did you feel the MyQuake? Oh my gosh, that was so awesome. Like, what'd you do? What'd you do? Everybody gets really excited, but then it subsides. And then all of your food and your disaster preparedness kit gets expired by like a decade. And you don't really have any water in your house because you used it for a party last weekend and you never refilled it because it's fine, there's not going to be an earthquake. And it's true, the earthquake hazard is not that big, so we don't have an earthquake every single day that's a magnitude 6 or above, but they do happen. And so this sort of technology is a way to get people more involved in what does it mean to have an earthquake. And so if you want to download this app, it has really cool features like, oh, hey, let's look at historical earthquakes around my area. There's a whole bunch of populated historical earthquakes in the state of California. You can also look at recent earthquakes worldwide. That's plugged in through the USGS earthquake database. It's published pretty quickly after a earthquake, sometimes quicker for during the day earthquakes, because the scientist on call is right there. I'm not struggling to find their glasses and their computer at 3 o'clock in the morning. So if you click on one of these historic earthquakes, so you can see over there we've got the 1868 Hayward earthquake, which incidentally, before the 1906 Great San Francisco earthquake, this was called the Great San Francisco earthquake, because Hayward was this sleepy little town, had some people, but mostly we're talking about flour mills and lots of horses and cattle. The larger population was still in San Francisco, so the population that was affected by this earthquake mostly was San Francisco, which is why it was called the Great San Francisco earthquake. But if you click on these sort of events, you can get little historical information. We have a lot of very interesting photos in the archive about Bay Area events specifically. But then, as you see in the little flag above, it says magnitude 7.0, intensity at your location 7. So what do I mean by at your location? Magnitude is a fixed number. It doesn't matter where you are. The Tohoku Oki earthquake in March of 2011 was magnitude 9. The 1868 Hayward earthquake was magnitude 7. However, shaking intensity is the intensity of shaking that you feel at your location. So if you are sitting right on top of the earthquake, you're going to get a much different peak shaking intensity than somebody, let's say, who is living in Los Angeles would have during that 1868 earthquake. They wouldn't have felt anything, even though it was a magnitude 7. They still would have felt nothing because they were too far away. And so a lot of people have heard magnitude 7, and oh yeah, Loma Prieta was magnitude 6.9, I know what that feels like. Or, oh yes, this other earthquake is magnitude 3.5, I know what that feels like. But you only know what that feels like because you were in a certain proximity to that earthquake. People who were in the mission in a liquefaction zone probably felt a bit more shaking than you did sitting on the peninsula or wherever you were at the time. And so what's a way that we can educate the public on what does shaking intensity 7 mean? Well, you just click through the app, and it has a whole bunch of different videos that shows different intensity ranges. So you can click all different historical earthquakes. Your phone knows what your GPS location is, so if you were in that location at the time of that earthquake, this is the shaking you would have felt. And so this is great to sort of educate humanity, and we want people to be aware of earthquakes and earthquake science, but what does that do for humanity? Where is our tech for humanity? And this is where my long video comes in, and I know it's long and I apologize, but it's so worth it. So instead of me getting up here and trying to give you a long boring spiel about what is earthquake early warning and why do we find that it's important, I'm instead going to turn it over to the lovely and wonderful Rachel Maddow.
Interesting.
Digital communications travel at the speed of light. Thanks to things like fiber optic cable, we can move information literally in a flash, and that is good, just in the abstract. But That is, it turns out, potentially life-saving. If the information that you are moving at the speed of light is notification that an earthquake is about to happen. Earthquakes happen in a specific place in the ground, right? Earthquakes have an epicenter. But you don't just feel an earthquake at the epicenter. The shuddering waves of motion in the earth from an earthquake, they emanate out from the epicenter of the quake, traveling at the speed of sound. So if you had the kind of motion sensors that detected earthquakes, if you had seismometers along fault lines all over earthquake-prone regions, when there was an earthquake, the seismometers nearest to the epicenter, they could register that an earthquake has happened, right, feel the shake, and then they could send a digital signal at the speed of light, notifying communities nearby that this traveling at the speed of sound tremor, this motion of the earth, is about to arrive. This is not a way of predicting earthquakes before they happen. It's a way of basically warning people that an earthquake has just happened and that they are about to feel its effects. Brace yourself. But this thing works. Scientists at UC Berkeley say that their Shake Alert to Earthquake Early Warning Project, it set off an alert. It did go off this weekend, during this weekend's large quake in Napa, California. It was about to be felt in Berkeley, and this is the alert that told them so. Watch this.
Earthquake, light, shaking, expected in 3 seconds.
They got a 10-second warning that they were about to feel the quake. And 10 seconds is not much time, right? But this brace yourself warning system, it works thanks to the simple fact that the speed of light is faster than the speed of sound, and earthquakes only move at the speed of sound. With more sensors in more places, they presumably deliver even more warning time. California's hoping to have that bigger system in place in the next few years if they can get it funded and finished. From the LA Times today, once fully developed, the system could give downtown Los Angeles 40 to 50 seconds of warning that the big one was headed from the San Andreas Fault, giving time for elevators to stop at the next floor and open up, for firefighters to open up garage doors, for high-speed trains to slow down to avoid derailment, and for surgeons to take the scalpel out of a patient. Giving your surgeon enough time to get the scalpel out of you before the giant earthquake starts shaking the operating room. That idea of a tectonically shaking scalpel inside your body somewhere, that is something you can never unknow, and I am sorry, but the idea that this warning technology, that it works, that it worked this weekend, in fact. It's not just on a drawing board somewhere, it is in effect, and it could be expanded and is being expanded. That is an excellent thing. They've got a system like this in Japan, they've got it in Mexico and some other places around the globe. California could get their whole statewide system done in a few years. God bless the geeks. They will save us all.
Yes.
So I'm sorry. She says that I heard that on Crown 4 just the day after. So Mexico and Japan apparently have these kind of apps even on their mobile phone. Is that correct?
So yes.
And why we don't have it?
So Mexico started their earthquake early warning system in 1985 after the large Mexico City earthquake that killed scads of people. And they have a very unique situation where they have a large subduction zone fault off the western side of the country that does predominantly the biggest amount of hazard. Mexico City is built on an old dried out lake basin, so you get all sorts of increased amplification factors due to this sort of basin sediment effect. And so you have a large earthquake happening really far away that's going to particularly affect your city because of the geology that your city is involved in. And also, you don't have great building infrastructure. And so they can routinely give people 60 seconds, which when you're talking about 60 seconds, that's plenty of time for people to exit these sort of questionable building stock. And when you have that large of a lead time, you don't need as sophisticated alert and algorithm development. So then Japan started its system because of the high-speed rail. The 1995 Kobe earthquake also killed scads of people. And the people who started working on the Shinkansen realized that they couldn't have a high-speed train and no earthquake hazard mitigation schema. And so they started working on that, and at first it was just for the Shinkansen, but then it got brought out to the rest of Japan, and now the Japan Meteorological Agency sends out alerts to the general public through apps, cell phones, TV, all sorts of different things. And what's sort of funny is there was a lot of Californians, in particular Tom Heaton down at Caltech, who wrote one of the first papers about earthquake early warning that then the Japanese went and took and built their system, and now we are a little behind. It's not just Japan and Mexico. Japan and Mexico have the two established public warning systems that have been working for a long time. They gave out alerts at the 2011 Tohoku Oki earthquake, so people got to duck cover and hold on before the magnitude 9 hit that area. Italy is working on earthquake early warning system. There's a whole European consortia called REACT that's working on it for the European Union. Turkey is working on one. Israel is working on one. We're involved in a sort of cross-border initiative in that whole Dead Sea area, Mongolia, Romania. There's a lot of people doing this worldwide. The kicker is that we have the opportunity to do this before we have a mass casualty event. And all of the other ones around the world, once you have this mass casualty event, all of a sudden the money is found to put in this sort of...
What about Chile? Do they have one?
Chile, I don't know of any system in Chile, no. And another reason why California is admittedly a bit behind has to do a little bit with our geography. We like to put people right on top of the faults. And so if we only have a little bit of advance warning because you're standing right on top of the earthquake, you have to have really fast telemetry and really fast algorithms, and you have to have really good station density, because it doesn't matter if your station is the fastest station with the fastest algorithm. If it's not sitting close enough to the epicenter, you're still waiting. And so that's why build out and station density is important. Is there another question?
Yeah, Jennifer, very important component of this, and I think that Rachel pointed out with some of those examples, 10 seconds is not a lot of time. And I would think there'd have to be a massive amount of training and education, maybe exercises, where you're in specific situations. Again, the surgeon with a scalpel in his hand, that's pretty dramatic, but as we know, an earthquake can happen at any time, and you would almost have to act automatically and know what to do. Because if you actually were thinking with those 10 seconds, you probably would screw it up.
Exactly, which
sense?
is why,
Yes.
So automation is key. This is one of the benefits of us living in the 2010s as opposed to the 1970s. Automation is key. You're right, the general person on the street, the best thing that they're going to be able to do is duck, cover, and hold on. They're not going to want to do all of these fiddly different things in their house and, you know, what am I supposed to do? What's my hazard mitigation plan that I can draft in the next 10 seconds? No. The general populace is going to want to duck, cover, and hold on. What we're doing, working with our technical users, is BART. Bay Area Rapid Transit now has earthquake early warning system ready. So when they get a trigger, they start slowing down the trains. So if you're sitting on the train, you don't have to do anything except try to cover in your seat as best as you can, because the BART operators have an automatic system in place to slow and stop the trains so that you have the least likelihood of derailment. In the hospital, you know, stopping the surgeon is great, but there's other things you can do. You can do an automatic bed count so that EMTs, when you're rushing to the scene after an earthquake, know which hospitals have beds. If you're in the middle of surgery, the scalpel thing is kind of scary, but one of the actual scarier things is force extubation. So if your gurney starts shaking during an earthquake, it's much easier for the anesthesiologist to sort of unplug the anesthesia. Just unplug you. Then you are a free person to float around, and you can do that for 60 seconds, and they can plug you back in. But if you are attached to a machine that's anchored to the wall, and your gurney goes that way, and you're force extubated, they have a whole lot more problem than just, I sliced you a bit with my scalpel. Elevator doors stopping at the nearest floor and opening. Firehouse bay doors opening so the trucks don't get stuck in. There are all these little tiny things that are not going to prevent a building collapsing or going off its foundation. It's not going to prevent a particular fire necessarily, but you're trying to give everybody the most automated tools that you can do so that the first responders don't have to deal with a whole bunch of people that got beamed on the head by these falling lights. They don't have to deal with a whole building of people stuck in an elevator. You know, they can actually deal with the real crises and the real recovery efforts. So automation is completely key. It is completely key.
From a practical standpoint for this 10-second example, presumably some sensor got it first and another one. Was it based upon the biggest detection where that one was, or it's traveling this direction, sensor A saw it, sensor B? How was it 10 seconds figured out?
So it is proximity to the quake. It's based on a trigger, and so if the seismometer nearest to the quake registers a trigger that it thinks is an earthquake, then it starts spinning up the system. And there's some algorithms that only require one trigger and a second station to confirm. There's other algorithms like our algorithm at UC Berkeley, which requires 4 stations to trigger. In the Bay Area, where we have pretty dense seismic networks, those 4 stations all trigger almost instantaneously. And so the actual sort of timing is dependent on your location. So I was in San Mateo. My warning was 12 seconds. And so what happens is there's an origin time of the earthquake. There's a time when the alert goes out. And the wave propagation speed with the origin time and the alert time gives you your countdown because it knows where I am.
So the origin time is defined by the first sensor that...
No, the origin time is the actual calculated origin time of the earthquake.
So there's nothing so it's being calculated by the sensors. There's no real time. It's a calculation. This is when it started, but it has to be 2 things. This is when it started, and this is where it is to provide that estimate of your 10-second warning.
Can you say that again?
To provide that warning, you have to know when it started and where it started.
Yes, so the thing that gets spit out for the alert is the origin time, the origin location, and the magnitude. So all 3 of those things are calculated at the same time. And it's that information that's used to do the rest.
One question, is it because of the sheer number of fault lines we have in California adds to the complication of the data collection?
It can add to the complication of the data collection just because you have aftershocks, and if your aftershocks are tripping one on top of the other, so if you have an aftershock that happens within 2 seconds of the main shock, or perhaps the first thing you characterized was actually the foreshock and not the largest shock. And so we tried to make our system smart enough so that if there is a main event happening, let's say magnitude 6 Napa earthquake, and there's an aftershock that's on either this same fault line or a nearby fault line that was just so close that sort of the strain causes some reshuffling on those plate boundaries, then we tell it to sort of don't alert on the 3, just continue with the 6. Whereas conversely, if the foreshock that gets alerted is a 3 and there's a bigger one that's coming, then change and go tell people about the bigger one. The other interesting thing is that you can, for a lot of these earthquake events, especially ones that don't rupture fully to the surface, the fact that an earthquake happened could tell you that there's a new fault that you didn't know about. I still have more stuff, guys. No, go ahead.
There's sort of a little sample of the MyQuake app where it gives you, tells you the size of what you're going to feel. Does this account for differing geology? Since I've been advised by family on the East Coast that they felt a fairly small earthquake that was a couple states away, because apparently the East Coast is much more of a solid mass, whereas out here it's all broken up by all these fault lines.
Yes, on a large scale, yes. We don't do fine grain like block by block sort of calculations, but the attenuation relationships that we run are California specific. And so this is one of the interesting things working with our partners in Cascadia, because they have very different geology up there. They're dealing with a subduction fault, and so things are different. And so one of the things that they're working on is how do you change all the algorithms to make them work up there.
Relating to that, would it, Loma Prieta earthquake, would it have notified the area around Cyprus or Marina differently than, it seemed like those we got
Not
lower
on that
rates?
kind of scale, no. We do have hazard models, and so in a sort of modern day repeat of the Loma Prieta earthquake, people in the Marina and Cyprus would know that they are going to experience heavy or shaking just from the models. And that's one of the things that we're working on doing in the future is more fine-scale, region-specific modeling or more path effects, like you do more fine-grained. Okay, so this is earthquake early morning, large quake. Now, what other things do you want to do? Where is our citizen science here? Right? Where's our local participation? And so I'm always going to go back to this smartphone. This is the new thing, right? Everybody's got one in their pocket. Can we use it? Surely it wasn't just designed to play Temple Run. There's other things that you can do with your smartphone. And one of the cool things that you can do in your smartphone is your smartphone has an accelerometer inside it. And so you can start measuring things with your smartphone. Now, if you look at frequency profiles just of the Earth in general, there's sort of a low noise floor and high noise floor of the Earth. The Earth is never going to be completely silent. We have tides, we have stuff moving, we have birds chirping. We have all sorts of things that make living on this planet wonderful, and so we have noise. And so you're not going to get better than this for a sensor that you have terrestrially on your phone. But what is the frequency spectrum of an earthquake? Well, here's a whole bunch of different ones, and you can see they have different acceleration ranges, and they have different, they have pretty much the same frequency band, but there's some that drop off at lower frequency ranges than others. So what does your cell phone do? So we took about 6 different brands of cell phone and did some noise floor tests on them. And so this is what we came up with. This is about as good as you can get, perfect, ideal world. This is your noise floor of your accelerometer in your cell phone. And so at first you say, well, that's actually pretty high, Jen. Like, what is that getting me? But do we really want to know about a magnitude 1.5 earthquake? You're not going to feel that. You can maybe start to feel a magnitude 2.5, probably feel a magnitude 3.5. You might stop drinking your drink. You're not going to duck under a table. Okay, around 4.5, 5.5, that's where stuff starts getting interesting, and that is where the frequency spectrum and acceleration range starts poking above the noise floor of the cell phones. So that's where we can start actually measuring what's happening. And the sort of long-term goal is all of these accelerometers in your phones. People replace their cell phones every year and a half because there's all sorts of new iPhone 6 coming out, new Galaxy 90 or whatever number they're on now. And so the goal is that these noise floors will become silence. There'll be protection at some point. We're not there yet. We're nowhere near there. I'm not saying it will be there in the near future, but conceivably it could go down. And so what can you do with the accelerometer in your cell phone? Well, you can start taking data because we're scientists and we like data. So you take your cell phone and you go ride it on the bus and then you go sit on your desk. This is where the noise actually starts being really apparent, is by just sitting at your desk with a cell phone in your pocket. It's getting quite noisier than the other things. You have your acceleration curves for walking and for running. So we can tell that there's a difference in all of these activities just by looking at the accelerometer on your cell phone. Yes?
Yeah, what was the cause of the noise floor in the cell phones? Is it a mechanical noise, electrical noise, sensor? So if you just isolated the accelerometer, could you get a better smartphone-based sensor?
I don't know. We only tested the noise floor like in the sort of chassis of the phone itself. We haven't really talked to
You can turn off all the other functions and just use the smartphone as an earthquake sensor to get that.
This isn't enough, to do that calculation. The noise she's talking about is the actual sensor itself vibrating just slightly.
And you can tell that all of these are a little more erroneous in the z direction than in the x, y direction, and that's going to be more apparent later. Okay, so we can characterize different discrete human activities on a cell phone itself on Earth. But can it look at an earthquake? And so conveniently, at Pier, we have a shake table, and it's normally used for building engineering tests, see if different new design features can be used for earthquake hazard mitigation. But sometimes, if they have space, they let us put all of our cell phones there. And so we've been working on this project in collaboration with Deutsche Telekom Silicon Valley Innovation Center, and they were the ones who kindly provided us with this whole host of cell phones. You can see they're all plugged into power, but they're all except one or two, I think, are freely just set on the table in different orientations. And so what does this data look like? Well, we have a reference high-quality accelerometer taped to the shake table, so we have some idea of what our control is. And then you just start taking data. And the raw data doesn't look so interesting, but what about filter data? This is starting to look pretty good. And with the exception of the z direction, which I said was 4, it's reproducing what the high-quality accelerometer does pretty well. And so if you zoom in, you can kind of believe more of what I'm saying. Again, the z direction is pretty much useless, but x and y components pretty much follow the reference material. And so we think that this is pretty good, at least first test. And so what can you do from there? Well, you do a whole host of different shake table tests on little tiny lab shake tables, on the big Pier shake tables, on all 20 of your different phones, and you can start building matrices where if you look at, okay, obviously the curves are not exactly the same, we're not doing any sort of like very fine-tuned curve fitting here, but if you just look at things like what is the vector sum of the peak acceleration versus the maximum number of zero crossings of your profile, and then you can start seeing that in your phase diagram, all of these different human activities start breaking apart from the earthquake signal. So this was very encouraging. And so then you can do other sort of table tests where you start ramping up the amplitude as a function of time, and you can see from the reference accelerometer, you get this very beautiful spectral pattern, which is very limited in your phase space in this upper left-hand corner. In the upper right-hand corner, you can see that your phone does a pretty good job. It's very noisy, but you can definitely tell where the main curve is supposed to be, and it behaves how it's supposed to. Now, then you look at the bottom figure, and you're like Jen, that bottom figure is pretty lame looking. I'm not really buying what you're selling me. And so this is a free phone. This is a free phone just sitting on the table, free to move around. And this goes back to the first part of my talk, where I was talking about you have problems when your reference frame and your instrument are moving and not particularly coupled to one another. And so you're like, does this really work? Can we have this work? The answer is yes. Yes, this does work. Because our grad student happened to have 2 of these phones running during the Napa earthquake. So phones were in Berkeley. This is a magnitude 6 earthquake. And so he was a ways away in Berkeley. And so the first thing that you would probably say on this plot is, gee, that looks pretty terrible, and that does not look anything like the earthquake nice textbook pattern you showed me on the very first slide. And I would say, Gee, you are exactly correct, because that's not the earthquake. That's our grad student, Chinkai, who leads the MyShake project, going about his day. Just hanging out, going about his day. And then at some point, around the 20,000 second mark, he goes home. And he puts his phone on the table, and like any really, really good grad student, he oriented that bad boy north-south before he went to bed. And then this is where the earthquake happened. And you're like, gee, I don't really see anything. Load up, Jen. There's your earthquake measured in the accelerometer of a cell phone. And so again, you can see pretty good east-west and north-south components. The up-down is not that great, but that is one cell phone. Now you imagine that we have our good distributed cell phone, accelerometer network through the California Integrated Seismic Network, who is monitoring earthquakes. We're trying to do earthquake early warning. We're trying to do definitive solutions on what the magnitude, location, and time for every earthquake. But imagine you can start looking into all these path effects that we were talking to. You can look at the difference between people sitting in the marina and the difference sitting in a lab in Berkeley if you have 1 million of these phones making these measurements at the same time. And so then you're not strictly doing this as an early warning thing. You're doing this as a citizen science project. How can we make our knowledge of what's going on better? Because if all of these phones trigger and start recording that earthquake and then send all the data back, you're going to get a lot more information than you would historically. And so this is being tested right now. We have the prototype working. We have the backend server, which is run by SenseOS, which is a Netherlandish company, Dutch company, who's running the backend server. Deutsche Telekom is doing a lot of the app writing, and as I said before, Chinkai Kong at our lab in Berkeley is running all the neural network algorithms that were behind this. So if you'd like more information about this project, come talk to me. And I'm only going to blow through two more projects, and then I'm all for questions. So what do you do? What do home tinkers? How do you extend the citizen science? This is an astronomy professor at UC Berkeley who has built a mini home alert system based on the Shake Alert project. He gets a Shake Alert feed. Shake Alert feed goes to his computer, but if he turns his computer off when he goes to bed, this thing is a Raspberry Pi unit hooked up to his home theater system, and so it receives the Wi-Fi signal and starts chirping out for earthquakes. One of our geodesist researchers at the Berkeley Seismolab has taken an Arduino set and has done a couple of different things with it. One is that she hooked up a bunch of LEDs to it, and so these light up depending on what your shaking intensity is, your location. If it's 2, lights up 2 lights. If it's 5, it lights up a whole bunch. And so you can start tinkering with all these little things that actually have real-world applications. So imagine this is like a set of gears or a generator that would be affected by heavy shaking. Well, so it receives a signal that an earthquake's coming. It powers down all the turbines, all of your turning gears, and then when the earthquake's passed, well, it just turns it right back on. And so these are just a couple of the sort of technology, more broader technology aspects than just the projects that you may have heard about in the news. So if you have any further questions, you can always reach me by email. Our webpage has an interactive map of all the recent earthquakes in California and various news features. And you can always follow us on Twitter at Berkeley Seismo, where we try to keep people up to date on different events. Thank you.
Seems like you'd have to have quite a bit of security to make sure that somebody didn't give you a false signal and you start turning off turbines, opening garages.
Oh yes, this is definitely something that is being worked on and heavily addressed, because that's the last thing that we want to have hackerspace. I'm not I am not at all involved in that project, but it's definitely one of the top priorities, besides getting everything robust and ready. This was much easier than back in the day, SneakerNet, where you could go to the instrument on the bridge and pick up the data. But now that it's all telemetered on the fly, security is definitely an issue.
What network are these sensors on? Like, are they on the internet or are they on a private, like all the sensors that are?
So the sensors are telemetered very different ways. The ones in California are all part of the California Integrated Seismic Network, which is a joint network run by Caltech, the United States Geological Survey, and Berkeley Seismolab. And so the data comes in differently depending on how the station is telemetered. Some of them are still SneakerNet, some of them are still 56K modem, some come over a Ethernet port, some of them are microwave, some of them are satellite. It really depends, and there's a different way to characterize things. But Doug Newhauser at our lab is the one who's in charge of all of that, so technical questions about that sort of thing, I would encourage you to ask him about.
So the USGS has a NetQuakes program. So
yes.
is it part of? Is this part of the same program, or is it completely separate?
So we are, UC Berkeley is not involved in the NetQuakes program personally, but we are involved in the fact that it's our collaborators and it's part of the broader network that we work on. But certainly NetQuakes project is going strong, and they have their own sort of citizen science things that they're trying to do with that as well.
So do they share data at all in any way? Or?
I don't think the NetQuake data is plugged into the NCDC database, which is the Northern California Earthquake Data Center. That's more of a Caltech run project, so I think all of it is fed into the Southern California Earthquake Data Center. I don't even know who to go for next.
Yeah, I have two questions since I got the chance here. One is, let's say you can sense, let's say, million Californian or 30 million or so, right? So let's say you can sense million phones, but you need to respond to them in real time. So how are you doing, you're applying neural network or some anomaly detection within a few seconds on those million feeds?
So this is things that we're working on right now, because the first thing that anybody who's worked with large amount of data before is that it's really, really easy to get things to behave when there's 5 phones. So we just ramped up from 5 phones running live 24/7 to about 30, and everything's starting to break. So for right now, we are in very early stages where we're just using this for recording and getting as much baseline data as we can. The next sort of ramp up stage would be, can you start to trigger the phones, and can you handle the volume of incoming from the triggers? The other problem is you don't want to kill people's data plan. So you don't want to actually have 24/7 open stream running to some data center somewhere and bleeding everybody dry on their data plan. And so this is why we see this more as a citizen science thing right now, and working through all the particularities of how do you integrate this for real time is ongoing, but definitely something we're hoping to do.